Okay, so I promised you that I was going to come up with an equation that relates the concentration of reactant to time for a first order reaction. All right, so what I'm going to do is start with this equation here. But remember, I said that I have to use calculus, so if you know some calculus, listen up. If not, you can skip down to where I actually get the equation. All right, so in calculus terms, we need to take these deltas here. All right, these deltas are finite differences, and we need to make them infinitesimal. So this delta A over delta T is going to become the derivative, the change in the concentration of reactant A with time. And this is really like it's an instantaneous slope. Okay, so instead of just having taking a finite thing, delta A, dividing it by delta T to get a slope, you're really taking the slope at a point, which is really like a tangent line to the curve. Okay, and the curve I'm talking about is, you know, the change in reactant with time, which has this thing. So the derivative is the slope at any point. I don't know why I'm telling you all this, because you don't have to know it, but it's all these different slopes as the reaction goes along. So dA dt is equal to Ka. And believe me that when I say that this is about the easiest equation that you could solve using calculus. So the first thing you're going to do is going to put the concentration of A on the left side, and this dt is going to go on the right. So we're going to kind of use algebra to make this minus dA over concentration of A equals K dt. And then actually I'm going to take this negative sign and move it over to the other side. Okay. So now what we're going to do, if you know calculus, is we're going to integrate both sides of this equation. And the integral of dx over x is equal to the natural log of x. So that's something that you learn when you figure out in calculus. So this is going to be the natural log of the concentration of A. And the integral of minus k dt becomes minus k, the integral of dt. So it's going to be minus k times the time, because the integral of dt is equal to t, but I have to add a constant because we only know what the integration of that is in terms within a constant. So I'm going to call the constant just constant, okay? And so we almost have an equation here, except we have to know what is this constant. We don't know what that is yet. Okay, so we want to know what this constant is, and I made a little mistake, so I erased a few things. So what we do know is that when the time is 0, the concentration of A is equal to the initial concentration. Okay, so we know that when the time is equal to 0, the concentration of A is equal to the initial concentration. So that means I can plug in a 0 here for the time. I'm going to do that. And I also know that the log of A, when the time is equal to 0, is equal to A0. So this becomes A0. Okay, but of course k times 0 is 0. So what this tells us is that the constant is equal to the log of A0. So I can substitute that back into the equation over here, and I end up with the log of A is the log of the initial concentration of A minus k times t. So that means I can put in any time I want. I can multiply it by the rate constant k. I can subtract that from the natural log of the initial concentration of A, and I will get the natural log of A. Now, we're going to practice using this equation, so don't get all scared about it, okay? So that's why I'm going to use activity 6 for. So here we have a reaction. A goes to products. And it's giving you what the initial concentration of A is. It's 0.6 molar. And it's telling you that the rate constant is 0.0320 inverse seconds. And I actually never went over the units of a first order rate constant. So I may as well do that just to show you. So if you have that the rate is equal to K A to the 1, a rate is always a molarity per second. It's a change in concentration over time. So the concentration units we use is molarity. So that means that we can use that to figure out what the units of a first order rate constant would be. Here we have molarity. A is in molarity units. So we basically can divide both sides by molarity, and we get 1 over seconds as a unit of K. So K, when it's for first order reaction, has units of seconds to the -1, or 1 over seconds, or S minus 1. Okay, so that's why we have that unit there for K. So here you're given the initial concentration of A, you're given the rate constant. And so the question that's asked is, what is the concentration of that reactant named A after 10 seconds? So that's what we're going to work on. So how are you going to work on this? Okay, so we're going to use the equation that we just got, that the natural log of A is the natural log of A0 minus KT, okay? And so what you're going to do, first of all, I'd like you to take your calculator and find the natural log of A0, okay, which is 0.6. So you need to find this, get this number on your calculator. And most calculators, you'll actually have a button that says ln, okay? And on most calculators, you'll just put this number in, and then put the 0.6 in parentheses, or I don't even think you need parentheses, and you should be able to get that value. So I want to just make sure now, as you're following along with this, that you do this on your calculator, and you find the natural log of 0.6, and you make sure that this is the number that you get. So you should be getting this number right here. All right. So now you all know you can take the K, you know how to multiply. We know that T is 10 seconds, so we're going to take 0.0320 seconds minus 1, right? This is the K. And then we have 10.0 seconds. That's the T. So we're looking for what is the concentration of A at 10 seconds after the reaction starts. So we're going to multiply these two numbers together, and that gives you 0.320. But the equation, notice, has a negative sign there, so we're going to take the negative of that. So we're going to take, since it's ln A0 minus KT, we're going to put in the negative 0.511. This is the log of A0 minus KT. So it's minus 0.511 minus 0.320. So if you combine these two numbers together, two negative numbers, we get negative 0.831. Okay, so what is this number? Okay, this negative 0.831, well, if we go back and look at the equation, that's the log of the concentration after the 10 seconds have passed. So that's the log of A, right, at T equals 10 seconds, minus 0.831. Now, obviously, this number is negative, okay? So it can't itself be the concentration of reactant, because it doesn't make any sense at all for a reactant to have a negative concentration. So how do I solve this equation to get the concentration of A instead of the natural log of A? So this is where I have to use the fact that the natural log and the E function are inverse functions. So I have to take E to the natural log of A. That gives me the concentration of A. right? So that is e to the minus 0.831, okay? So in order to get the concentration, I need to take e to the number I get here, or, so on your calculator, you might have an e to the x button that you'll use, or you might have an inverse natural log. So what you're really trying to do is this. Inverse natural log of 0.831, or e to the minus 0.831. That's, put that in and see if you can get this answer. Okay, so the answer, which is the concentration of A at t equals 10 seconds, is 0.436 molar. Okay, so you can see that it is less than the initial. So if it's not less than the initial, then you did something wrong. So you have to make sure that you know how to do that. Okay, so the next question is, how much did the concentration of A change in that 10-second time interval? So we started with 0.6 molar, and at 10 seconds, the concentration, so this was the initial, at 10 seconds, the concentration of A was 0.436 molar, so we just subtract, and it ends up with 0.164 molar is the change in the concentration of A in 10 seconds. Okay, so now let's do it again, okay, because practice makes perfect. Okay, so we're going to use the same equation. The log of A is the log of A naught minus KT, but now we're going to put in 20 seconds here. And we have the same rate constant. Okay, so we're going to multiply this together, and we get negative 0.642. Meanwhile, we have the same value as we had before for the log of A0, minus 0.511. And this is minus KT, so we have minus 0.511 minus 0.642. If you add that up, you get negative 1.153. Okay, so that is the log of A at t equals 20 seconds. Now, in order to find out what is the concentration of A, well, again, we either have to take inverse ln minus 1.153, otherwise known as e to the x. So we're really taking e to the minus 1.153, okay? And we should get the same number. That should come out to 0.316 molar. Okay, and how did the concentration change from 10 to 20 seconds? If we go back and we look at what we had after 10 seconds, it was 0.436. Oh, you know what? This shouldn't have a 0 here. That's absolutely wrong. Okay, so we had 0.436 at 10 seconds, and now here we have 0.316 at 20 seconds. If we take the difference there, we get 0.120 molar. Okay, so let's take a look at that. So for the first 10 seconds, the change in the concentration for that first 10 seconds was 0.164. The change in the concentration for the next 10 seconds is 0.120. So what's happening to the reaction? It's the same length of time that passed, but we have a smaller amount of reactant that reacted in that time. So this indicates that the reaction is slowing down, which we know happens over the course of a reaction. But our nice equation that we got from calculus accounts for all of that. Okay, so what's the concentration of A after 30 seconds? Well, going to use the same equation.